functions.
Hi, everyone. I'm a postdoc currently in Edinburgh, and this is a work I'm doing with two friends who are not much older than me, Dhruv and Jinhan. Dhruv is an expert on submesoscale ocean dynamics and structural functions in surface drift datasets, and Jinhan is an expert on Lagrangian mean series. We will focus on two sets of drift datasets that are both located in northern Gulf of Mexico. They are called GLAD and LASER respectively. And here we are showing the histogram of the drift observation locations in the two campaigns. And obviously they span over a similar spatial region. And as a feature of surface drifters, they are always jog on the ocean surface as sketched here. As they are moving around, they report their velocities through GPS tracking. And the data product we use have velocity observations interpolated at 15-minute temporal intervals, which is very fine for ocean timescales. The data sets also span over a vast spatial range between at least 100 meters to 100 kilometers. So the main novelty of this work is to combine the fine temporal and spatial information of these drifted data sets by applying a Lagrangian filter onto some operations of the second-order structure functions. Finally, I want to remark that a main difference between GLAD and LASER data set is that the GLAD data is taken in summer and the LASER is taken in winter. And the second-order structure function just mentioned is defined in this way. Yes? Are there some questions? Oh, it's defined this way. Suppose we have these drifters on the ocean surface. Oh, sorry, I'm hearing some reflections. Probably my computer, sorry. Yeah, suppose we have some ocean drifters on the surface denoted by the red dots here, and then we can form a lot of drifter pairs denoted by these dashed lines. And then suppose we focus on this specific drifter pair, and then we can draw a vector that connects the two drifters. And this vector connecting the two locations of the two drifters in the pair is what we call the separation vectors. And we use a polar angle where r denotes the distance and alpha denotes the polar angle. At each temporal snapshot, we can project delta u, which is the velocity difference measured by the two drifters in the pair onto two directions, along and across the separation vector, delta u and delta ut, where L denotes longitudinal and T denotes transversal. And structural functions are defined based on the assumptions of horizontal homogeneity and stationarity. By that, we mean that if we do a statistical average over all the available snapshots and all the available drifter pairs, then the average quantity is assumed to be a function of the separation vector only. It's not a function of the starting location or the timestamp of the snapshot. Under this assumption, we can define the second-order structure functions accordingly, which are just products of delta u and delta ut. And as a note about all notations all over this talk, whenever you see a subscript, it's denoting some component. It's not going to denote any partial derivatives in this talk. And the temporal operation we'll do on the drift observations is going to follow the Lagrangian filter framework. It can be illustrated in the following. Suppose we have a particle whose trajectory looks like this. In our case, it could be the trajectory of a surface drifter. Then we can filter the trajectory into a mean and a perturbation component. The mean trajectory is plotted in the thick line here, and the perturbation is this excitum. And then according to this mean and perturbation trajectory, we can also find a mean and the perturbation velocities that are consistent with the mean and the perturbation trajectories respectively. And crucially, in the Lagrangian mean framework, both of these velocity components have to be evaluated along the mean trajectory, not the actual trajectory. We'll go back to this later. And this is an illustration of what we actually do in the surface drift data sets in GLAD and LASER. Plotted here are the power spectra of the velocity magnitudes. And we can see that, so the blue line is the full power spectra, and the yellow line is the high pass field, which includes all the inertial peaks and super inertial motions. And the low pass component contains a lot of the sub inertial motions. And the filter we apply is a Butterworth filter that's cut off at 1.5 days, and it's the same in the two drifter data sets. To follow the Lagrangian mean framework, we also need to filter the trajectories. And to do that, we just track every drifter specifically. And along the track of each drifter, we apply the same Butterworth filter to get an analogy of this sick line. And then after we get these mean trajectories, we compute the separation vectors again. And then we can plot, I'm showing here the histogram of the separation vector computed based on the mean trajectories. And this is just a zoom up of the histogram. And as a pedagogical thing, I want to also show the effect of taking the mean of the trajectories for this data set. So this is the same histogram of the separation vectors, but it's computed based on the raw trajectories. At a glance, it looks very similar to the one based on the mean trajectories. But if you zoom in, you can see a lot of difference. For example, a lot of these wiggles here are smoothed out after the Lagrangian mean is taken. So this is a general feature of taking a Lagrangian mean of the trajectory, in that the large scale features are going to be very similar, but there will be a lot of differences in the smaller scales. And then we will do a Helmholtz decomposition onto the velocity second order structure functions. By that, we mean that following the Helmholtz decomposition theorem, the horizontal velocities can be decomposed into a part that's induced by phi, which is the potential function, and a part that's induced by psi, which is the string function. And the potential function induces purely divergent motion, and the string function induces purely rotational motion. So for each drifter pair, we can decompose delta U, which is the velocity difference measured by the two drifters, dynamically into a part that's induced by the string function only, which is purely rotational, and a part that's induced by the potential function only, which is purely divergent. And for now, we'll assume isotropy, which is some assumption I will relax later in the talk if I have the time. Under isotropy, we'll assume that the structure functions are not functions of the separation angles. They are only the functions of separation distance. So under this simplification, we can have this simple formula that actually computes the second order structural function induced by the rotational motions and divergent motions respectively. This formula was first established by Buehler, Callias, and Ferrari in 2014 for power spectral data. And finally, before I show the results we see in surface data set, I want to note a technical caveat. This is what we call angle weighting, which is to accommodate the fact that we can see that the separation vectors are not actually uniformly distributed in angle. If they are uniformly distributed in angle, we should see rings, not these fine features here. And the traditional way to compute second order structure functions is to take unweighted ensemble average over all the observations available in each bin of separation distance. For example, suppose we have 6 observations located at this separation distance R. The traditional way is just to sum them up and divide them by 6. But obviously, this is going to introduce systematic error because it will be biased towards 2 and 3 and 4 and 5 because they are more densely distributed in angles. So recently there has been a simple fix to alleviate this error by introducing angle weighting. And the idea is very simple. This is how it's done in data sets. We can divide all the angles into a few bins in the angle, and then within each angle bin, we compute the ensemble average respectively, and then we can average over the estimates within each bin. So for example, for this bin we have 1, and for this bin we average between 2 and 3. And in this bin we average between 4 and 5, and then we average over all the bin estimates. So now I can finally show some results in the surface data set. So again, what we are doing here is that first we apply a Lagrangian filter onto our data sets. And what I'm showing on this slide is what we'll get after applying a high-pass filter. And as a reminder, the high-pass filter keeps all of this, which is including all the near inertial and super inertial motions. And we are doing this on the GLAD data set. And here is the result after we do the Helmholtz decomposition on the high-pass filter data. And we can see here that the green line, which is the divergent component of the second order structure function, is always larger than or equal to the rotational component. And I was very excited to see this because it suggests that the dynamics here is consistent with linear waves. Let me explain why I think so. So by under linear theory, we can ignore the derivative term in the momentum equation. And based on the linearized momentum equation, we can derive that the time derivative of the string function is related to the potential function in this way. And consequently, the ratio between the divergent and rotational structure functions is going to be proportional to the ratio between the intrinsic frequency and the Coriolis frequency squared. And in the ocean, we know that the intrinsic frequency should be generally larger than or equal to f. Therefore, we should expect that the divergent structure function should be larger than or equal to rotational function, provided that we can do the linearization. And I think this data set suggests that since the divergent structure function is always larger than or equal to the rotational function, it means that the linear theory is consistent with this. And another interesting thing we see is that at the larger scales, the divergent structure functions start to be very close to the rotational structure function. And that's also consistent with linear theory because at large horizontal scales, if you recall the dispersion relationship, the intrinsic frequency is going to be very close to f. And therefore, at the largest scales, which is here in data set is almost mesoscale here, we should expect indeed that the two structure functions are going to be close to each other. And finally, I want to note that in this data set, in the wave component, we can see that it matches pretty well with r to the 1 slope in the structure function, which roughly correspond to a k to the -2 slope. And there are many theories that are consistent with a k to the minus slope in the wave component. And this is the same result. This is what we get if we do the same thing for the laser data. So we are computing the high pass field and then we do a Helmholtz decomposition again. And again, we see that the divergent component is always larger than or equal to the rotational component. But it seems like at scales larger than about 1 kilometer, the structure functions start to decorrelate in that they are becoming flat and fluctuating. And we speculate that this might be related to the increased submesoscale instabilities in the laser data set as compared to GLAD. And another discovery made, which is quite striking to me, is that this is what I just shown for the laser data set for the high pass field. And again, when we compute this, we evaluate the structure functions on the mean trajectories. However, if we do the same calculation, if we do the high pass again, but if we evaluate structure functions on the raw locations instead, this is what we get after we do the Helmholtz decomposition. And this is completely different dynamically speaking. And we can see a clear dominance of rotational component everywhere. And it doesn't make much physical sense to me because I don't know any theory that can explain a clear dominance of rotational components in the waves. And this is almost certainly a signature of the balance flows. And theoretically speaking, if you do Lagrangian filtering of velocities, and then if you evaluate them onto the raw trajectory instead of the mean trajectory, then you will lose a lot of nice properties, such as, for example, if you have a materially conserved quantity, such as the PV, it won't actually conserve along the raw trajectory. It will only conserve along the mean trajectory. I think this is something Hossein might talk about later after me. So going on to the low pass field,
5 minutes.
what we see in the laser data. And we can see that at scales smaller than equal to 1 kilometer, which is comparable to the scale of France, there's an equipartition between rotational and divergent components. And we're actually not aware of any theory that are consistent with this yet. It probably has something to do with France, but we don't know for sure yet. And at larger scales, we see again dominance of the rotational component over divergent component. I want to note that we don't see similar things in the raw component that has been published before. If we only look at the raw component without doing the Lagrangian filtering, we see a dominance of the divergent component at smaller scales, and now we know that this is due to waves. And if we look at only the balance flow, we actually see an equipartition. In the GLAD data set, we see something similar. And so this is another interesting thing we found, which is that if we compare the low pass component between laser and GLAD, they are actually very qualitatively similar in that they both have equipartition in the low-pass component at smaller scales between the rotational divergent component and larger scales, they are dominated by rotational component. And more interestingly, we can see that the scale at which they transit from equipartition to the dominance of rotational component is very similar between GLAD and laser, and this is not what I have been expecting to see actually, because the mixed layer thickness is very different in GLAD and laser. They can vary by a factor of about 5. So, and we can see that the transitional scale is not varying by a factor of 5. So that means that whatever is set in the transitional scale, it's not related to mixed layer depths, which is pretty surprising to me. And if you know some theory that can explain this, please let us know. So finally, I want to mention that we also consider to relax the assumption of isotropy, and I think I will skip this and jump to the result. And so shown here, the purple and green lines are what I've been showing you all the time in this talk, but the added pink and blue lines are the anisotropic component. And if we look at the raw data without the filtering, we can conclude that the anisotropic component don't seem very significant at any scale. But if we look at the anisotropic components in low pass and high pass field respectively, we can see that in the low pass component, it's more significant, especially at smaller scales, which may be again related to fronts. And at high pass components, we can see that it's pretty significant at the larger scales. So the take-home messages of this work is that in terms of method, we have developed a way to combine spatial and temporal information by combining the Helmholtz decomposition and Lagrangian filtering of the surface drifter dataset. And as a technical caveat, we have applied angle weighting, which is a simple idea to avoid bias from non-uniform angle distributions, and it's useful even if you are only considering the isotropic modes. And we also find a striking example that demonstrates that if you are doing this Lagrangian filtering, it's better to evaluate everything on the mean trajectories instead of the raw trajectories. And in the laser and GLAD data set, we saw a bunch of interesting observations. For example, the high pass component is consistent with linear wave theory, especially we can see a proof of the near inertial waves in the GLAD dataset. And in the low pass component, we find that the transitional scale seems to be insensitive to the seasonality of the mixed layer thickness. And finally, we can see anisotropy more in the frequency filtered fields if we, as compared to the raw fields. And as a trailer for the next project, we are trying to do similar things for third-order structure functions, which can reflect energy transfer rate. And this is inspired by recent work by Zhu Van Jinhan. And I noticed on the abstract book that there will be a related talk tomorrow led by Julia. And the main idea is that under some theoretical constraints, we can decompose the slow fast and slow slow transfer rates of the third order structure functions. And we'll welcome collaborations on this. Thanks. I'm happy to take questions.
Yeah, thank you for the interesting talk. Do we have any questions from the audience or from online?